So let's start with this new seminar in the ESQPT 2021 seminar. Before I introduce our next speaker, Qian Wang, I would like to make an announcement so that everybody knows that next week it is non-labor in Huelva, so there will be no talk next Friday. You have a free Friday. Enjoy your free Friday, and I hope that you enjoy even more the following talks. Today we have a talk by Qian Wang on excited state quantum phase transitions. This is not a surprise. This is main subject of the series. He will speak about these transitions from a phase space perspective. I met Qian in the QPTN meeting in Padova. I invited him. I was at that time the convener of one of the sessions, and I invited him because he has published a nice work on Loschmidt-Eco and excited state quantum phase transitions. And since then we got in touch and we have also worked together. So it's for me a pleasure to host him today in our series. Qian is a young guy. He studied PhD. He got his PhD in the University of Science and Technology in Hefei, China, and then he got since 2015 he got postdoctoral experience first in Peking University, then in the Shanghai Normal University, and presently he's a lecturer in Zhejiang, sorry for my pronunciation of Chinese, Normal University. Also, he has an appointment nowadays in Maribor, in the CAMTP-Center. So he will speak about this phase space analysis or ESQPT. So Qian, all yours.
Okay. Thank you for invitation, and thank you for that introduce. And today I will first actually I have two talks. Firstly is this talk, as we can see, is about phase-based analysis of excited state quantum phase transition, and the other one is about OTUC study of excited state quantum phase transition. Okay, let's start the first one. Today, for the first one, this is the afterlife. I will first introduce the phase-based distribution function. Then I will introduce the Husimi distribution function, which I will use in our study. And then I will introduce the models, two models. One is Lipkin model, and the other one is the coupled top model. And then I will show the results. Short summary and outlook will give at the finally. Firstly, I will give a short brief of about phase-based distribution function. As we know, in quantum mechanics, a quantum state is described by a density operator. With this density operator, we can calculate the expectation value for an arbitrary operator. We can, from the density operator, we can get the expectation value of an arbitrary observable. However, from the classical work of Wigner shows that the quantum mechanical, we can also represent the quantum mechanical in phase space, in classical phase space. The main tool for this, for the phase-based formulation of quantum mechanics is the phase-based distribution function, which can be considered as a phase-based or classical counterpart of the density operator. However, due to the other P and Q are non-commutator in quantum mechanics, so the phase-based distribution function are the distribution functions are the quasi-probability distribution function, not the joint probability distribution probabilities functions. So if we have this fast-based distribution function, we can get we can calculate the average of quantum operator of this. Here we have introduced the function f in order to consider the non-commutator between operator p and q. Of course, this function, we can choose this function, different choose of f corresponding to different fast-based distribution function. Generally, from this expression, we can get the general form of the fast-based distribution function. Of this is complicated, but from this distribution function, we can get by replace the density operator rho with an arbitrary operator a, we can get the operator fast-based formula the operator a fast-based counterpart of operator a in this formula. And as I said before, we can choose f to get the different f will give different fast-based distribution function. And in this in this table, I show some examples for different choose of f and the corresponding distribution functions. The simple one is f equal to 1. This choose of f gives the famous Wigner distribution function. And of course, we have different the other form of f and corresponding to other form of fast-based distribution function. And usually the most popular distribution function is Wigner distribution function, and also the Husimi distribution function. Of course, in the quantum optical field, the popular one is the global P function or Q function. And for a true distribution, joint probability distribution function, they should satisfy these properties. These properties. Firstly, is bilinear in the wave function. That means f, the function, that function f should be independent of psi, and also we should also that distribution function should also be really function and also negative, and also the marginal distribution should be corresponding to the distribution in the position space or in momentum space, and also should be complete fulfill the complete also norm condition. However, as we said before, the fast-based distribution functions are the quasi-probability distribution functions. So therefore, no single probability fast-based distribution function can satisfy all these conditions. Actually, in this table, we summarized the above mentioned distribution functions, the properties of above mentioned probability functions. It can be seen that no one can fill the above mentioned the full properties. Anyway, because of the fast-based formula of quantum mechanicals use classical language to study to describe the quantum mechanical or quantum phenomena. So it's very popular. It has been applied in various physical fields, such as quantum optics, quantum chaos, and also quantum condensity matter physics. In particular, fast-based distribution have been used to study the phase transitions in quantum systems, such as ground state phase transition and also Anderson localization to delocalization transition. So in this, in our study, we trying to understand the ESQPT used by employee the fastbest distribution function. The main function we use is the Husimi function. For a given quantum state rho, the Husimi function is defined as the overlap between the coherent state and the quantum state. In our system, we study the spin system. So the coherent state we use is the SU2 spin J coherent states. It can be right. Its expression. This formula gives is its expression, and it satisfies this closure relation. And of course, in order to visualize the Husimi function in classical phase space, we should parameter psi in the by using the classical phase variable p and q. So we use this transform. Of course, this transform restrict in this area is a circle area, and by combining this closure relation of coherent states and this parameterization of psi, we get the normalization condition of the Husimi function. It's like this, and this is a Husimi function. And we use the Husimi function to study the ESQPT in two quantum many-body systems. The first one is the okay, I forgot. From the Husimi function, we also, to quantify the property of the Husimi function, distribution function, we also study the second momentum of the Husimi function and the Wherl entropy of the Husimi function. We also consider the marginal distributions of the Husimi function and the corresponding second momentum and the Wherl entropy. And the model we studied is the first model we studied is the Lipkin model. It's can be considered as a full connected Ising model. This is the Hamiltonian. It's this is a collective operator. This is a control parameter. From this Hamiltonian, we find the total momentum, angular momentum is a conserved property, is conserved quantity, and also the parity is also commutated with the Hamiltonian. So because of this two conserved quantity, the numerical calculation will be easy. And this model has a ground state of this model has a quantum phase transition at kappa critical point at kappa equal to 405. It separates the paramagnetic phase from the ferromagnetic phase. Besides this ground state quantum phase transition, this model also shows an ESQPT at critical point with critical energy equal to 0. This ESQPT can be characterized. The feature can be manifested in the density of states. In this figure, we plot the eigenlevel energy spectrum of the Lipkin model and also the corresponding density matrix. It can be seen that the energy levels collapse at the critical energy, and also this means the density of states will choose a Casper at the critical energy. And the second model is the coupled top model. It describes the interaction between the coupling between the two large spins. This is the model's Hamiltonian. Here the psi is the coupling strength between two spins, and J1, J2 is two spin is the angular momentum operator of the first spin and the second spin. For this coupled top model, it's the Hamiltonian is commutated with this should have score. computed with the total angular momentum of the first spin and also the second spin, and also it's computed with the parameter. The exchange between the first spin and the second spin doesn't change the Hamiltonian, and also the Hamiltonian is conserved under the parity. And also this this model undergoes an ground state quantum phase transition at psi equal to 1. It separates the ferromagnetic phase from the paramagnetic phase. Besides this, it also exhibits an ESQPT at EC over J equal to positive and minus 2. It's also can be found from the density of states of the model. However, different to the Lipkin model, in this case, the ESQPT is manifested in the derivative of the density of states. This figure shows the energy spectrum of the model. This is the density of states of the model. This is the first derivative of the density of states. It can be found at the critical energy. This derivative of the density shows an obvious peak, cusp-like shapes. This is two models. In our study, we will focus on the ESQPT of these two models, and we consider the quench dynamic. That means we firstly prepare this. Set the control parameter equal to the initial value with the Hamiltonian, and also set the state of the system at the initial state. In our study, the initial state for both models are set to be the ground state, and then we suddenly change the control parameter from the initial value to the final value, and then we concede the evolution of the system and the governed by the post-quench Hamiltonian. In our study, for the Lipkin model, the quench protocol leads to the Hamiltonian changes from the initial one to the final one. Of course, by changing the quench strength, we will take the system to the critical energy. The critical quench is given by this formula. And for the couple top model, we also change the control parameter psi from psi 0 to psi 1. And by changing the value of psi 1, we can take the system to go to the ESQPT critical energy of ESQPT. The critical quench coupling is given by this expression, and then we consider the time involved and governed by the post-quench Hamiltonian, and then we consider the Husimi function of rho t, and we also study the long-time average. The Husimi function of the long-time average state is given by this this expression, and from this we can calculate the corresponding Husimi function like this. And then we first show the results in the Lipkin model. We consider for the Lipkin model we can get the Husimi function of rho t as this form. From this we can see the Husimi function is strongly depends on the transition amplitude between the initial state and the nth eigenstate. This En is denotes the nth eigenstate of the post-quench Hamiltonian. This figure shows a different time, a snapshot of the Husimi function at different time. It can be with the control parameter below, with the coupling strength below 8 and above the critical coupling strength. From this, we can see the evolution of the Husimi function shows obviously distribution, behaviors in different phases of the ESQPT. In particular, at the critical point, the Husimi function shows a large extension in the classical phase space. We consider the long-time averaged state and study the long-time averaged state Husimi function. For the Lipkin model, we can get this simple expression for the long-time averaged state Husimi function. From this, we can see it's also depends on the transition probability between the initial state and the nth eigenstate. And this three figure shows the long-time averaged Husimi state or the Husimi function for different control parameter. This one is below the critical one. This is at the critical coupling. This is above the critical coupling. We can see for the when the coupling strength is smaller than the less than the critical one, the Husimi function is localized in the classical phase space. However, at the critical point, it shows a largest extension in the classical phase space. And this figure shows the marginal distribution of the Husimi function in position space and in momentum space. From this, we can also see at the critical point, it shows a particular shape.
May I make a question?
Yeah, sure.
Yes, one question, because
okay.
when you change, you can study the expectation value of your initial state in the final Hamiltonian, and you know the energy of the final states in the final. Are these figures which you are showing from the Husimi function, perhaps they map to the classical trajectories in the classical dynamics?
Yes. This is a Husimi function, and I also calculated the classical. Use the classical case, a classical Hamiltonian equation to calculate the classical trajectories, and we found it's very similar.
Mm-hmm. Yes.
The classical trajectory is very very similar to this Husimi distribution.
Mm-hmm. Thank you, Qian.
And to quantify this, we calculate the second momentum of the long. To quantify these features we observe in the Husimi function, we calculate the second momentum of the Husimi function and the Wherl entropy. And this is our numerical result for different control parameter kappa, and also for different system size. The solid line for system size n equal to 200, the dashed line for system size n equal to 400. And from this, we can see all of this, both of M2 and W shows the system at the critical point. The Husimi function shows largest extension in the phase space. Moreover, we consider the scaling behavior of the M2 and the W at the critical point. From this, we can get we found for the M2, the scaling is a parallel scaling with the system size, while for the W, it shows a logarithmic scaling behavior. And the scaling exponent show for different critical coupling strengths is shown in this figure. It's it's almost around 0.6. And also from this, the maximum extra value of M2 and W, we estimate the critical coupling strengths for different kappa, and we found this in good agreement with the numerical results, analytical results. This dashed line shows the shows the numerical analytical results. And this is for the Lipkin model. The second, and also, okay, finally, we also choose the Lipkin model in for the in Lipkin model, we also choose the marginal the second momentum and the Wherl entropy for the marginal distributions. As we see in the previous figure, it also shows different drastic changes at the critical point. The dashed line, green line, indicates the critical point. This is the result for the Lipkin model. The second model we concede is the couple-top model. For the couple-top model, different to the Lipkin model, for the couple-top model has 2 degrees of freedom. So the first base of the couple-top model actually is 4-dimensional. To visualize the Husimi function, we consider the projected Husimi function of rho t. We consider the Husimi function in the the classical space of the first spin, like this. Here, 0, 1 per t is the density, is the reduced density matrix of the first spin, and this is our numerical results. We can see the Husimi function, the time evolution of the Husimi function shows a similar feature as we observed in the Lipkin model. For the when the coupling strength is small, the Husimi function is represented by 2 localized Wherl packets. But at the critical point, it shows a large extension as the time increase. And also we calculate the long time average reduced density matrix and for the first spin, and then we calculate the long time average projected Husimi function, and the final result is straightforward to get this result. And also we see this is also strongly depends on the transition probability between the initial state and the nth eigenstate. And here 0, 1, n is a reduced density matrix of the first spin. And this is our numerical result. It's also very similar to the results observed in the Lipkin model. However, for this case, as the system size is small, so not like in the Lipkin model, in this case, the distribution has a large, the widest of the distribution is large, not like in the Lipkin model is very small. For the Lipkin model is very small. And also we consider the second momentum and the Wherl entropy for the long time average projected Husimi function, and we see the same also as we observed in the Lipkin model. We also see the M2 and WCT M2CT shows a dramatic change as the system crosses over the critical point. And we also calculate the scaling behavior of M2 and W, and we see the we see the M2 is also follows the power law, and the W is also follows the logarithmic scaling behavior. We also calculate the scaling exponent as a function of XR1. We see it shows is a large value around the critical point, and we calculate and we estimate the critical point from the use the minimum value in the derivative of the critical exponent, and we also found a good agreement between the numerical results and the analytical results. And this is for the this is for the M2 and the W for the marginal distribution behavior. It's also as shows a dramatic change as the control parameter passes through the critical point. In this case, critical point is 1.5. And okay, this is our work. And for a brief summary, Husimi function is, of course, for both models, we see the Husimi function exhibits different distinct dynamic behaviors in different phases of the ESQPT. So this means we can use the Husimi function to detect or probe the emergency of the ESQPT. And also the scaling behavior of M2 and the W reveals the characteristics of the ESQPT. For the outlook, we see the relation between the features of the behaviors of the Husimi function and the first order ESQPT. And also we trying to understand the phase-based multifractal features of the quantum states at relation and the ESQPT, the relation between them. This is the first talk. The second one I want to show another work we have published 2 years ago. It's about the out-of-time order correlator and the ESQPT. We use the out-of-time order correlator to detect the ESQPT. For the out-of-time order correlator, it was firstly introduced by Lipkin and Ovchinnikov it's very long ago. In this paper, they use this quantity to study the superconductivity. And later, science from 2015, it started to revive. It's revived by the Kitaev and also some other researchers. The out-of-time order correlator is comes from the out-of-time commutator. CT is defined as this is average over is a commutator score average. By expanding this expression, we get these terms. The first one is we call is a constant term. Usually, for example, if WT and V0 is the sigma, is a spin Pauli matrix, we will get FD is equal to a constant. And the out-of-time order correlator is this two term is actually the out-of-time order correlator. It scales, it decrease with increased time. And so this is the definition of the time of the correlator. And to calculate it, it can be considered as the overlap of two states. One, both of them start from the same initial state, beta, but involved in different way. For the X is involved. Firstly, we measured V at the beginning, then involved until time T, we measure W, and then reverse the Hamiltonian and involve until time T, we get the state X. However, for the state W, it's also start from the initial state beta, but it's involved in a different way. It firstly involve until time T, then we measure W, then we reverse the Hamiltonian and then involve until T and measure V, we get the state Y. Then the FT, OTOC can be considered as the overlap between these two states, X and Y. For the generally, FT is the really part of FT have this behavior. It's decrease with increased time. And the decrease rate is called the quantum Lyapunov exponent. Actually, the decrease rate is closely related to the classical Lyapunov exponent. It can be found from the out of time order commutator. For this from CT, because in the classical limit, CT reduces to the Poisson brackets. And for the Poisson brackets, we get this for the chaotic system, we will get this expression. So we found the quantum Lyapunov exponent is closely related to the classical quantum classical Lyapunov exponent. For the canonical ensemble, some works have found the Lyapunov quantum Lyapunov exponent has an upper bound given by this. And also the OTOC has been measured in various experiments. It uses tripped ions and nuclear magnetic resonance platforms. In our moreover, the ESQPT, the OTOC has also been used to study the phase transition in IC model. This is the result for the IC model, and this is the result for the both Hubbard model. For both of them work, we can see the OTOC can be used to detect the the ground state QPTs. And in our study, we consider the OTOC. We use the OTOC to study the ESQPT. To do this, we study the ESQPT in the Lipkin model, and we choose the W and V as the Sx, the x direction of the angular momentum, rescaled Sx, and we after crunch. We involved the WT, the system, and consider the WT give us this. Then we consider the FT, and the FT is given by this. It's very complicated, and we calculate FT for different control parameters. This is the control parameter, the value of control parameters less than critical point, and this is for equal to critical control parameter, and this is larger than greater than the critical control parameter. We can see the FT shows different behavior in different range phases of the ESQPT. In particular, at the critical point, it's very complicated. And we further, because of this, we consider the long-time averaged OTOC, and we calculate the numerical results showing this this figure for the different lambda and the different control parameter, and we find the F long-time averaged OTOC can be used to detect the ESQPT. In particular, it behaves as an order parameter for the ESQPT. Moreover, we find the critical point, the F long-time averaged OTOC at the critical point behavior follows the power law scaling behavior, and the F long-time averaged OTOC follows the power law with the distance of the critical point with the critical exponent given by this. This is the time averaged long-time averaged OTOC for we change the critical control parameter. However, for the ESQPT, it's defined as a critical the integer, the divergence behavior in the integer spectrum. So we further consider the microcanonical OTOC. In this case, we consider the OTOC averaged over in different eigenstates, and these three figures shows our numerical results. The first one is for the eigenstates, is actually for the ground state. The second one is for the critical states, and the third one is for the energy for the states with energy larger than the critical energy. And from this we can see we also find remarkable different behaviors for this microcanonical O2C. This means the microcanonical O2C can also be used to detect the ESQPT. We further consider the long-time averaged microcanonical O2C. From this, we found in this case we found the long-time averaged microcanonical O2C also behavior as a outer parameter for the O2C, and we also found some scaling behavior for the O2C around at the critical point and around the critical energy. This is our second result, and this is our final summary for this work. Firstly, the ESQPT has leaves significant imprint on the O2C dynamics, and also the presence of ESQPT and its critical point can be detected via the O2C, and also long-time, in particular, the long-time average O2C behaves as an outer parameter of ESQPT. The open question is O2C dynamics in other kinds of ESQPTs, such as ESQPT in Dick model, because in Dick model they have besides ESQPT, they also have integration to chaos transition. And also the second question is the requirements that W and V should fulfill in order to make sure the O2C performed as a detector between different phases in quantum many-body system. Because in our study, we found if W and V choose SZ, we cannot get the O2C, the evolution of the O2C will no difference in different phases of ESQPT. So the condition, what kind of condition W and V should fulfill is still an open question. Okay, that's all. Thanks, and thanks for attention.
And mute. Thank you, Qian. Thank you. You get the price of one. That's
thank you.
That's a very good offer. So we have two different talks. So as Qian said, now it's there is some time for questions and comments and remarks and whatever you think appropriate. So is there any question for Qian? There, I can see a hand. There is Paulina. Paulina, please.
Thanks for the interesting talk and for the interesting outlook also. I have two questions regarding the Husimi distribution. The first question, you said that it is positive, right? And that one can also use a representation not only of states, but also of observables. Could you please tell me whether the representation of the observables is also positive?
Sorry, let me see. You mean the Husimi function?
Yes.
Then?
So you said in the if I define a distribution, phase-space distribution, right? I can use it both to represent states and to represent operators.
Yes.
And when I represent states by means of the Husimi distributions, the Husimi distribution will be always positive, right?
Yeah.
Now, if I represent an operator in the same framework by a phase-space distribution, is this phase-space distribution also positive or not?
I think it's depend on what kind of observer.
So you think it's not necessarily positive, yes?
Yeah.
Okay.
Actually, for the general form of an operator in right in the phase space is like this, in this formula. So depending on the observer, it can be positive and also negative.
Okay, thank you. And the second question is related to the one of Professor Hirsch. So I apologize if I just did not get the answer. I think that if you look at the Husimi distribution of a state in the mean field or in the thermodynamic limit, then you will get in the limit exactly the classical phase space trajectory of the initial state.
Yes.
They coincide exactly, right?
Yes.
Okay, thank you.
Yeah, thank you.
Okay, thank you, Paulina. Then are there more questions for Qian? No more questions for Qian. I have one comment for Qian. In the case of the OTOC, I think that when you mentioned the different ways to proceed in this field, because I think it is an interesting, it's very interesting quantity that nowadays has raised a lot of interest. Is what happens when the systems have, apart from having coupled systems, you mentioned first order quantum phase transition, like in the decay model. There you can see first order on a coupled system, but also even in the Lipkin, you can study first order phase transition, which is not yet coupled. That will be interesting. And also we are interested, and in fact we're working together in extending these two models towards higher dimensionality, like the Vibron model or the IBM, to see how this, because this introduces substantial changes compared to the Lipkin, because one tends to think that the type of transition, the second order phase transition between UN-1 SON is the same in the Lipkin, Vibron, and there are at least for the OTOC there are many differences. That's an interesting. And I think that's an interesting way to pursue and to explore.
Yeah.
So are there any other question or comment for Qian? If not, we'll thank our speaker. And remember that next week there will be no seminar, and we will announce a seminar for the following week. We are still closing this with the next speaker, but so next Friday no seminar, and we will go back in 2 weeks. Okay, so thank you again, Qian. Thank you very much for your participation and for your talk. And remember, everybody who is interested in giving a talk about ESQPTs, we are open to suggestions of collaborators, or any of you that is here can also join the speaker set. Okay, thank you very much.